Welcome to Approximating Functions with Taylor Polynomials. So recall in the previous video, we saw that the Maclaurin polynomial approximations for f of x equals e to the x pretty quickly got to be very good approximations. Near x equals 0. Furthermore, as we went to higher and higher degree, the approximation sort of expanded the interval over which it was a good approximation. So as our degree got larger, the interval over which it was a good approximation expanded. And so we wind up getting a theorem that kind of formalizes this just for Taylor series in general, or sorry, Taylor polynomials in general. And this theorem is called Taylor's theorem. So we can expand on this idea with Taylor's theorem. So Taylor's theorem says that if f is a function whose n+1th derivative exists on the interval I, and C is contained in I, and if C is contained in I, then for each x in I, there exists z sub x between x and C such that f of x is equal to the nth degree Taylor polynomial at x of x at f at C. I'll do that on another line, actually. So is equal to Pn of x plus some Rn of x, where Rn of x is equal to the n plus first derivative of f evaluated at z sub x over n plus 1 factorial times x minus c raised to the n plus 1. So this is different. We're plugging in z sub x instead of c into that n plus first derivative of f. So this is not quite the n plus first Taylor polynomial. So here, p sub n of x is the nth Taylor polynomial of f at c. Right. So we get this slightly odd, it's an odd function of x, and that z sub x itself is kind of a function of x. So z sub x itself, I'm going to cross off what this means. Z sub x itself is essentially a function of x. Right, so zx is going to differ from one x value to the next. So essentially, we can find z sub x's that make f of x equal to the nth degree polynomial plus this weird additional n plus first term. Then we also have and the absolute value of r sub n of x is less than or equal to the max of the absolute value of the n plus first derivative of f evaluated at z all over n plus 1 factorial times the absolute value of x minus c raised to the n plus 1. And here, the max as we run through all z in the interval I. So we take the maximum value that n plus first derivative takes over the interval I. Okay, so essentially we have the max of the absolute value of the n plus first derivative evaluated at z. This refers to the the absolute value of the maximum value of the absolute value of the n plus first derivative on the interval I. Okay. So this is what we get for our formula. It's kind of odd, but essentially what this means, or what this tells us, so what this tells us is that since f of x is equal to p sub n of x plus r sub n of x, this means that f of x minus P sub n of x is R sub n of x. And therefore, the absolute value of f of x minus P sub n of x is the absolute value of R sub n of x. So, we get that the difference between f of x and P sub n of x is bounded by the same thing that Rn was bounded by. So is bounded by the max of our absolute value of the n plus first derivative of f over I. That gets divided by n plus 1 factorial. And then we times by the absolute value of x minus c raised to the n plus first. Power. So essentially we have a formula that puts a bound on the error of our Taylor polynomial in terms of its ability to approximate. So this gives us a bound on the error of P sub n of x as an approximation for f of x. So this isn't necessarily the most pleasant looking formula for a bound. It's maybe a little difficult to comprehend. So in the next video, we'll go ahead and do an example where we actually put a bound on our error of our Taylor polynomial estimate. And then we will follow that up with figuring out what degree polynomial would we need to use to get our desired, to stay within a desired error. So again, in the next video, we'll do some examples using this slightly odd formula.